Could you please dim the lights a little? Is that possible? So that
you want the lights turned off on the whiteboard?
just maybe, yeah, yes, there will be more contrast. Thanks.
Right. Well, thanks, Dora. So one of the things that I do is I teach on subject at Western Sydney Uni, which teaches high school calculus to first year engineers. They do a lot of word problems in this subject, and in one of the class tests I learned that the Golden Gate Bridge is, well, one student said it was 1.5 k's long and high rather, and another student said it was about 2 millimetres long. Obviously it's a lot bigger than it was when I was there. In some tests like Don mentioned, the Bladesville Bridge in Sydney, well, the width of the Parramatta apparently ranged from a couple of angstroms to a few k's wide. It may have been predictive modelling looking at the effects of climate change, but these are a few other things were going on, and I just started thinking about, well, why are students so hopeless at word problems, and why do they give such, just such ludicrous numbers? Well, what's actually going on? So how do I try this? That works. Okay, so I tried chatting with people and we came up with a few possible options. Now, I don't believe the fourth one. These students, whatever else we might think about their backgrounds and so on, I think they do care. They do want to succeed and they care quite a lot about doing well. As to the first two, they do generally come in with very poor mathematical backgrounds, and they have very weak numeracy skills. And if you give them, a calculation, that they generally can't look at it and have any idea whatsoever what sort of number they're going to get out, even to an order of magnitude. But on the other hand, if you ask them point blank, how wide do you reckon the Parramatta River is? They'll give a really sensible ballpark figure. So I don't think that it's their weak mathematical backgrounds and poor numeracy that's going on here. Third one is a possibility. These word test results, the students might be panicking, and you can't think when you're panicking and you say all sorts of silly things. But I've seen the same sort of thing going on in tutes, and hopefully they're not panicking during tutorials. So I decided to think about it further and look into it. So the first thing is the common knowledge that word problems are harder. There's in a normal maths problem, say you might start with an equation, you've just got to solve the equation somehow or process the algebra or whatever. In a word problem, you've got that extra step above that. You've got to go from something and create that equation for yourself, which is harder. Formally, you're actually mapping from one language to another language. You're going from a set of symbols, in this case words, and you're translating them into another set of symbols, the maths. But in order to do that, you've got to assemble all the concepts. You've got to analyse it logically, synthesise it, figure out the procedures you're going to use, and then apply the whole lot of it. And you've got to be able to do every single one of those steps. If you can't do one of them, you get one wrong, you don't get the word problem out. So word problems are really hard, no question. But that still doesn't explain why students are trying to tell me that the Parramatta River is a couple of angstroms wide. All right, so students generally don't realise that their answers should make real-world sense. Believe it or not, this is plastered all over the literature, and it seems to be a universal phenomenon. Interestingly, though, it also appears to be learned. It gets worse with age. Which hopefully means it can also be unlearned. Now, just to make sure I get some real proper school-approved ICT into my talk, I've got a video here. I just want to show you a few seconds of it. This was a study done by Kaminski. He gave this nonsense question to a bunch of 8th graders in interviews, and what he was interested in was whether they said the question's nonsense or whether they tried to answer it, and that's his figures up in the top right. So I just want to show you a few seconds of it, of students trying to work out the answer. And if you watch the numbers...
Thank you. Can you tell me, how did you know to divide?
Because it doesn't say the difference, or it doesn't say the sum, or the product or something.
I see. Okay, thank you very much.
Okay, that's as much as I wanted to show you. But what you'll also notice, apart from the entertainment value, is that they all went for numbers like 25 or 15. In fact, in his study, the biggest number that came up was 120. They're all picking numbers that might be a shepherd's age. This study was, how do I get out of here? I knew I was going to get stuck here. There we go. Okay, so this problem was was posed to some older students in China. And interestingly, the results were very similar. About 3/4 of the students tried to answer it, only about a quarter said it's a nonsense question. They're the same sort of proportions as we saw in the younger American students. However, what appeared here was that while most of the numerical answer students went for things like 25 because it sounded like a sensible number, other numbers like 125, 130, even 956,000 started appearing. Now this has worried me a great deal because other people have also reproduced this study and they were reporting similar sort of findings. And so I thought, gee, what would happen if I tried this on my students? So I slipped this into one of their cheat sheets. Sorry, Don. So I had to ask this student what was going on. And rather happily, this was their attempt to use mathematical notation to say that the shepherd's age is somewhere between 0 and infinity because you can't work it out from this problem. So you can see we have a different issue here with using mathematical notation. But in terms of this question, it was an appropriate answer. And very happily, 100% of my students who looked at this question said you couldn't answer it and it was silly. Now, I'm not going to purport that my cohort of students at Western Sydney are somehow way better than the other students. There's something else going on here, obviously. And the thing is that problems presented in a class come with unspoken social expectations. Here's a couple of things that people said. One is that the students' main objective in this study was not to make sense of the question or even to answer it correctly, but to give an answer that will satisfy their teacher. And the students believe an honest answer like, I can't do it, isn't going to make the teacher happy, so they pick a number at random in the hope they're left in peace. And then April Sue was the researcher who did the study on the Chinese students, and afterwards she reported that the students were feeling like they didn't have intellectual autonomy and weren't free to question the teacher due to their respect for authority. And I guess the take home of all of this is that this is a huge issue in word problems. There's all this other stuff going on that's getting in the way of the students actually engaging with the problem itself. Here's another example. I think you'll like this one. A college student in a German-speaking university was given the following question in their oral, which was to show how one can measure the height of a skyscraper using a barometer. The student's answer, well, you take the barometer with you to the top of the roof, tie these well longer and go rest the road. Then pull it back up and measure the length of the roof. This length corresponds to the height of the skyscraper. Good. Now, the examiner's report apparently was scathing. But you have to ask why, because this student's answered the question and it's a method that's going to work. Okay, the thing is that in oral exams in physics and in word problems in maths, both the teacher and the student play a well-defined role according to a set of unspoken expectations. And in this particular example, the only expectation that this particular student neglected was the unspoken one to answer the question in a situationally defined way. They were meant to have the barometer as the central feature of their solution, and they were meant to use physics that they just studied. But neither of those were spoken. And in maths word problems, there's an absolute multitude of unspoken assumptions. Right? They can solve it. There is a correct answer. Their teacher knows it. All of the information given in the question is both necessary and sufficient. And you can see all of these playing out in the Shepherd question. The question is well formed, again, assumed by the students in the Shepherd question. The work relates to stuff recently studied. It just needs application of the correct formula. the answer is a nice round number. There are studies in which people have gone around adjusting their answers and trying new methods until they got the whole number solution, and that was right. The question contains cues as to how to answer it. You saw that in the little girl on the video. She went for division because she couldn't find anything that said to add, subtract, or multiply. And an answer is required. Okay? And the thing is that students end up operating on these unspoken assumptions rather than on the problem itself, like the study where they actually gave this to a teacher and the teacher adjusted and played until they came up with a nice round number for the answer and decided that had to be it because the fraction ones couldn't have been right. Students are actually working on these assumptions and not addressing the problem. And the other side of this is it's actually easier to solve a problem than it is to actually understand the problem and really solve it. Here's a common approach to word problem solving. I just pulled this fairly randomly off a website, but you'll find this and the variations anywhere you're looking in teaching handbooks and so on. You know, read the problem, highlight the keywords that tell you what to do, visualise it, figure out your operations, write the equation, solve it, check the answer, which tends to morph itself into rip a couple of numbers out of your question, pick your formula, stuff them in, and write down the answer. Don't think too hard, just do it. And so you end up with this thing where mathematical problem solving becomes completely devoid from reality because we're following this process and we're not trying to understand what we're doing or tie it back to reality at all. Here's another example. This question's about a Venn diagram. 30 students were asked if they read or play an instrument. Some read, some played an instrument, some don't do either. And we get 3 questions based on that, 1 both question and 2 XOR questions. 56 students were each given one of those 3 sub-questions to answer. And of the people who got both question, they all got it right. Isn't that lovely? And of the 2 that got the XOR questions, about a quarter of them got it right. And so we infer that both questions must be easier than XOR questions. Well, not really, because if you look at what's going on, for the first answer, that all the students said the answer's 4, which just happened to be right. But most of the other students who got it wrong also said the answer was 4. Where's 4 coming from? Can you see it? If you look at the numbers in the question, don't worry about the question, forget everything, just look at the numbers. There's 30 over by itself, and then you've got 3 numbers over kind of clumped together somehow. Now, they're smaller than 30, so let's just add them. Oh, look, we get 34. 34 is bigger than 30. Let's take the difference, and hey presto, some of the time it's right. Okay, so it's easier to do something like this than it is to worry about actually understanding and addressing the problem. The last thing is that solving word problems involves taking risks. It involves trying out something new, and this can be anxiety-inducing, which of course can lead to avoidance in students. So students will do whatever they need to avoid these problems, including picking a number at random. Okay, so what to do? My interest in all of this is applied. How does this change one's practice? What can you do to help? All right, so first thing is obvious, explicit modelling, like any sort of teaching. Collier's is still the definitive work on solving word problems, as it is for solving any sort of problem in general. There's an absolute multitude of frameworks out there to help students solve word problems, and word problems are very hard and frameworks are helpful. Some frameworks are better than others. Very few of the frameworks, though, have Collier's step or the reflective step. Some of them will have a check your answer step, but checking your answer is not the same as reflecting, thinking, how good is my solution? Are there other solutions? Are there other problems where I've used this sort of methodology? Does it lend itself to these other areas? We're synthesising your knowledge and deepening it. And I think that's a really important part of this model and teaching word problems. So when you are modelling, I think it's important to explicitly model all 4 steps. Okay. Do things that mess with the unwritten assumptions. We know that the only way to address misconceptions in students is to let them loose on a problem that goes wrong for them when they use their misconceptions. Then they're forced to reconsider and open up to new options. And so if you can give them some sort of word problem that breaks when they use their assumptions, then hopefully they're going to be more open to considering a new approach, like understanding the problem, for example. You know this one already, not all word problems are created equal. This is a quote from Merryn, who says that many textbook maths problems are not intellectually challenging because they're formulated as semantically poor disguised equations rather than as thinking stories or situation problems. Since 1988, this has been well addressed, and there are increasing numbers of really good word problems in existence, but there's also heaps of terrible ones out there too. So choose your problems wisely. Build in reflection, build in time for reflection, build in the expectation of reflection. A long quote. Do I have time? Maybe. All right.
2 minutes.
Okay, I can do it. All right, so Grave-Mayer, when talking about why students give you rubbish answers, says the first cause is in the stereotyped character of common word problems, and the second cause is in the classroom climate. Stereotyped problems don't ask for reflection. In fact, the character of the problems is such that the students have to refrain from realistic considerations. And in general, the classroom climate is one that endorses this separation between school maths and everyday life reality. The students aren't expected to reflect on their answers. The focus is on getting the right answers quickly and not on reasoning about the represented real life situation. Teach students to have intellectual autonomy, to have confidence in their capabilities and take risks, even if that includes disagreeing with the teacher, arguing back, whatever. Experiment with different teaching strategies. We know that presetting students' expectations affects performance. Russa did a study where he divided students into 2 groups, gave them a word problem. The first group were told the word problem was easy. The second group were told the word problem was hard. The second group substantially outperformed the first group. Teaching strategies that encourage questioning and reflection. So here's a couple of thoughts that people raised looking at the Shepherd problem. This was a teacher commenting on this work, simply said, I wonder if the results would be different if the students were broken into small groups and asked to solve the problem collectively. This might provide enough courage to overcome the influence of authority. Also, considering a quarter of them tend to get it right, then each group would probably have some answers it right. Maybe this would change the outcome. And Kaplinsky himself suggested, well, what if after we ask this question, we then say, another student said the answer was 35. How can we tell if that student is correct? So again, it's
Not far enough, John.
I'll hide grounds here. I'll stop now.